entanglement is this strange quantum property where multiple quantum systems can have correlations which are stronger than you can ever get within a classical probability theory. And this is why it's kind of more powerful than anything you can get within a normal classical traditional computing framework. But how we actually get entanglement to where it's supposed to go is difficult. So here I show basically a few steps that we can use in order to get entanglement across longer distances, such as in this example on the right. So in this example on the right, we're imagining that the middle node, the one that is connecting the other two, is a repeater. And a quantum repeater is used for swapping entanglement. But what is entanglement swapping, and how does the entanglement get there in the first place? The first step in doing this is what's called elementary entanglement generation. So if you have nodes that are connected through fiber or through some sort of channel, the idea is the first step is to get entanglement between those nodes. If they're close enough, this shouldn't be a problem, and you can do this in various ways. With all of these steps, I should mention, these are subjects that we can give an entire talk on. And so I'm not going to be able to go into any details on any of these specifics, but this kind of shows you the general progression of what you need to get there. So if you can generate entanglement between your local nodes, if you can do this, but it may also not be good enough entanglement for your purposes. Entanglement can have a quality or a fidelity. If this is the case, what you need to do is called distillation or purification. This involves taking multiple entangled qubit pairs, which are weakly entangled, not enough for you, and combining them into a single pair that is strongly entangled, that is good enough for your purposes. Once you get this strong enough entanglement across your neighboring links, then that's when the quantum repeater comes into play. So the quantum repeater is in charge of taking, as we can see here, these qubits in the middle and doing an operation on them, a measurement, which destroys the entanglement individually, but transforms it to entanglement across the larger link. It sort of extends the entanglement, it stitches it together. And so you can imagine that if we have many of these repeaters, each one can do the same thing, right? We can distribute entanglement across all the individual links, and then each repeater can do their swaps. And in that way, we can extend entanglement across a longer distance by stitching together these individual entanglements. Once that entanglement is there, then you can use it for what you want. Like we said, we can maybe use it for sensing. If you want to use it for actually sending qubits from node A to node B, you can use what's called teleportation. So as opposed to having to try and send a qubit all the way across that large distance, if you can already get that entanglement, then you can do an operation on one end, send a classical message, and then the other end will be able to receive that qubit state exactly. And so in this way, using entanglement as a resource which gets used up, we can send quantum states over long distances, and in this way, quantum network over long distances. So that was the basic steps of getting your entanglement where it's supposed to go.